Hello everyone. Just give it a couple seconds and then we can get started. Um, okay, cool. So I'll just keep this open. So if you're at home, well, yeah, just connect through you'll scan the QR code or just go to slido.com and type in that code. From here, you'll be able to answer the questions that some of the multiple choice questions that we'll have during the lecture. You can ask some questions of your own. And during the break time and right before the session ends, we'll be going through these different questions that everyone has had. You can also upvote other people's questions. So if you see a question that that you're going to ask as well, just upvote the other person's questions, and then we'll move all the way to the top. Alrighty. I'll have that up there for a little bit more. Right before we get started, I'll quickly talk a little bit about ATAR notes. So since 2007, ATAR Notes has been providing free resources to all students just to even out that playing field. And I think since 2015, we've been running these lecture series. They used to happen like in person, but I think for the last couple of years they've been happening online. I think this year they might have a few in-person ones. Can't remember, but yeah, we are still running some of them online, as you can see. Yeah, so I really think these lectures are really good like revision material. You guys get these slides as well, so if you don't take down all your notes, don't worry too much. You can use these slides as well as part of your notes. So these are provided to you on that website. There should be a little link area where you can get your notes from there. Big shout and thanks to Latrobe for helping us run our lecture series. Do check out their sort of like lectures and stuff as well. They're pretty cool. So ATAR notes, we have study notes, we have these lectures, we have a discussion forum, we have some free like videos online that are little like tutorials. We have like ATAR calculators, so you can chuck in your study score and use last year's like sort of like aggregate to estimate your ATAR. Not entirely accurate, but it's like a good way to see if you're on the right track. Or set your goals as well. We've got like study strat articles and so on. But yeah, do check out the website. We did like kind of revamp it. It's kind of cool. Yeah, I think it'll get you to re-sign in and stuff. But yeah, like migrate your account. But yeah, okay. But yeah, we've also got things like Ed Unlimited, which is basically like an online library. So you've got a bunch of study guides all in one place. We have TuteSmart, which is our tutoring service, and yeah, we have study guides, which you can buy anywhere. Okay, so a little bit about me. So my name's AJ. I got an ATAR of 99.15. I graduated last year. And right now I'm at the Australian National Uni studying a Bachelor of Philosophy in Biochemistry. It's kind of a weird way of like, I don't know, the way they have their degrees planned out is sort of weird. But yeah, so I'm basically doing like a research intensive degree in biochem. If you guys have like any questions about uni as well, chuck those up in like Slido. But yeah, cool. All right, so that's my dog Loki. Like we named him from like Thor. I love reading random stuff. I guess like as long as it's not like work related and it like lets me procrastinate, I will read it. But yeah, cool. I think one thing I forgot to put up on these slides is my email. So if you guys do have any questions, feel free to email me. It's just aj@tutesmart.com. I should be able to annotate this. Yeah, I can, but okay. I'm not gonna bother with that. It's gonna like make me like draw it out. It's gonna be really annoying. Maybe I'll draw it out at the end if we have some time. Okay, so today's plan. We're gonna try to spend about. Sorry about the coughing, by the way. We're gonna try to spend about an hour on statistics, and then we'll have a little bit of a break at 10:30. And then we'll start covering complex numbers. And after we're done with complex numbers, we'll move on to vector calculus, kinematics, and dynamics. Okay, so yeah, so we'll be taking your questions through Slido. like I said, oh, let me see if I can get the laser pointer out. Okay, cool. So like I said earlier, upvote other people's questions that you also want to, be curious about. Just keep in mind when we covered these topics here, it's just a brief revision. And we might not be able to get through all the content, and that will also be sort of flagged throughout the slides as well. And that's because a lot of these slides here aren't meant to be gone through. They're just there as like summary notes for you guys. So there are some summary slides. I think the next one, there's a summary slide somewhere for statistics. I'd definitely say like save that, print that out, and chuck that into your bound reference. Okay, I'll also talk about a little, like at the end, we'll also talk a little bit about, what to put in your bound reference, whatnot. Okie dokie, let's get started. Alrighty, statistics. We can, basically split it up into two different main topics. So the first one is, linear combinations of random variables, and we also have hypothesis testing. So the reason I say we split it up into two topics is because the first topic, linear combinations of random variables, is basically all we're adding on from methods, probability, and sampling. So we have normal methods, probability, and sampling, and now we're talking. That's kind of annoying. Okie dokie. I'll just check if the stream is up and running. Okay, cool. So yeah, this is quite important. And there's different formulas that we apply for each case. So it's quite important you guys know the difference between these two. And I'll talk about how we can work out the difference between these two as we go on through today. All right. So hypothesis testing, I think conceptually, it's like the most challenging topic. But once you get it pat down and you have like the working out basically memorized, and you've done enough questions to the point that it's like muscle memory, I think its marks are pretty easy to like pick up on the exam. You're almost always guaranteed a hypothesis testing question at the end of your exam. I think they like to put the probability statistics question on special exam 2 right at the very end. That being said, you might have a hypothesis testing in your exam 1. So last year in 2021, we did have a hypothesis testing question in our exam 1 from memory. Okay, so with hypothesis testing, we need to be able to map out our normal distribution. So yeah, that's why, written down, drawing is important. So if you guys remember from methods, all those funky drawings, let me see if I can, yeah. If you guys remember what the normal distribution looks like, it's a little bit like this. That's not symmetrical, but it is symmetrical down the middle with the normal distribution. The reason I say, it's good to draw out things with the hypothesis test is to like block out areas and know which area you're working with. But that's basically it. Cool. I'll just get rid of this. Okay. Another thing we need to understand is null and alternative hypothesis and errors. You're hardly sort of assessed on errors, but every now and then they'll get you to find the probability of a type 2 error. And so I'll walk you guys through that as well. Okay, so this is the summary sheet. This is all methods 3-4 knowledge. You will have, all of this except that is methods 3-4 from memory. Definitely have this somewhere down in your book. I think this is given in the formula sheet. And this might be given in the formula sheet as well. But everything else, I definitely chuck in. Also, here, this just says, this is just meant to say, you're meant to only find your standard deviation through your variance, right? So don't ever try to skip your variance calculations to the standard deviation calculation. Find out your variance first and then take the square root of it, just because you're less likely to make a mistake in that case, instead of taking the square root at the start and then having to plug everything in. Okay, cool. So this is the summary sheet. That's in the slides. Make sure you take this down. All right. So when we talk about linear combinations, I think we can sort of go through it with a pretty cool example. So the devil of gambling offers you two options to win money. So option 1, you roll a die once right? And then you'll double the times the number, like you'll earn 2 times the number you roll. So for example, if you roll your dice once and you get 6, you're going to double it and you'll get 12. But you'll roll, and number 2 is you roll a die twice and you'll earn the sum of the numbers you roll. So this is like saying I roll a die once, I get 6. The second time I roll, I get 3. And so then it's 6 plus 3, and then I earn 9. So we want to know which game, 1 or 2, yields a more consistent income. I'll give you guys a couple seconds to have a think about this. If you're not sure, that's all good. I just want you guys to have a general idea of how we can work through this. So the key is using a times x versus x plus x plus x a times. So I'll give you guys a couple seconds to have a think, and then we'll have a look at the solution. Okie dokie. Hopefully you guys had some time to think about that. Think about the different ways you could have sort of, attempted to solve this. So the hint here is here. We want less variability. We want the outcome with the lowest variability. All right, so let's see how we work through this. So let's consider the first option. So let's define, so when we start a probability question, we should always define what our variables are. So in this case, let's let x the number that turns up when rolling the die once, okay? The reason we can do that, and the reason we can define it as the same variable, is because with this, we can define it as 2 events, and with this, we can just multiply it by a factor. Let me see. So this is case 1. So we're going to be rolling the die once, so our outcome is x, and then we're going to multiply it by 2. So we'll have 2x. And now here, this is the second case. We're going to roll the die twice, but we need to add up the numbers rolled. So we're going to add x plus x. The reason we can't merge them together as 2x is because they're not really the same outcome, right? In this case, x can be 6, right? So then our outcome will be 12. But in the second case, this can be 6 and this can be 4. So then obviously we can't put them together and simplify them to 2x. Okay. So you'll see that when we have multiple events, we add them. But if it's just being doubled, we can put the scalar multiplier at the front. Okay. So the first thing we want to do is have a check of our expected variable. So when we find our expected variable, we can sort of find the expected variable of x. I don't know why I said variable. When we want to find our expected outcome, sorry, I don't know why I said variable. Strange. When we find our expected outcome, we can take the e of x plus this one's e of x, right? So we can split this into 2 and we get 2e of x. So then really this is equal to this. But when we look at variability, we have 2 different formulas, if you guys can remember. So we have this formula here, and we also have this formula here. So there's 2 possible outcomes with variability. So in case 1, we have to use 2x. So we get 2 squared variance of x, and we get 4 times the variance of x. In this case, we have to apply the second formula, this one, and we end up with variance of x plus x, and we have to split this up into 2 different variances, and we get 2 times the variance of x. So we see that option 2 yields a more consistent outcome because its variance is half of option 1. Cool. Hopefully that made sense. So what does that mean? So what does that mean in terms of us running the calculation? If we were to do this question another time, how would we actually solve it? So the general rule is written here. So if you only do x once, but it then scales by a factor of a, then you have to do your combination variable is equal to a times x, right? Because you've run your outcome once, and then it's going to change by some factor a. But if you run or expect the event a times, then you have to add the outcome a times. That's because this x is potentially different from this x and this one and so on, right? Because remember, this is not just a variable; it's a random variable. So its value is defined over a set of a bunch of random outcomes, right? So for that reason, we can't say that this x and this x are going to be the same. So we can't stack them and combine them like this. So we actually need to separately add them a times. So just to recap, if you do x once and it scales, then you do y is equal to a times x. But if you're running the event a number of times, then you need to add the event separately a number of times. Okay, so if we chuck that into our formula, you see that our expected value is the same, right? But our variance varies greatly. So the variance of y in case 1, we get a squared times the variance of x. So I'm using this formula here. But then when we add them a times, we're going to be doing the variance of x plus the variance of x plus the variance of x, and that's going to happen a number of times. So variance of x is just multiplied by the constant a. Cool. So there is a big difference. And when we use these to combine our linear variables, and when we try to use a calculation through these, we can change our answer greatly depending on if we actually do the right one or not. But yeah, so know the difference between our variances, and note that there's no difference between our expected variable. Okay, so what we need to do from this is we need to identify which one, a of x or x plus x plus x plus x, right? And VCE will never tell you which case it is, but you're always going to have both cases on your exam. But yeah, you need to decide if the question has independent components. If they are independent components, so for example, with this one, you're doing 2 independent trials, right? You're rolling the die once and then you're rolling it again. That's 2 independent trials. If you have 2 independent, or if you have multiple independent components, then you're adding your variances like this. But if it doesn't have independent components and all the components are linked together, then you're doing this multiply sort of thing. Okay, cool. Hopefully that makes sense. So yeah, this is the way that it'll probably be worded. So find the probability of total x and y is, or you're adding things together, that's going to be an independent thing. But if it's the same component 3 times, then you're going to be multiplying because they're not independent. Okay, have a go at this question. I'll get the poll started for that. We have a couple questions to get through today. Okay. Have a crack at this. I'll give you guys 1 minute to do this. So 9:54. Or yeah, 9:53 and 30 seconds. And then that's when we'll stop and I'll go through the working out for this. So once you get your answer, just make sure you chuck it into Slido. So then we can see how, the results sort of like tally up. Okie dokie. Hopefully that was enough time for everyone to have a crack at this question. So generally with multiple choices, the rule that I like to follow is 1 mark per minute. And obviously that's like an ideal rule. It's not going to happen in every single case, right? There are going to be some multiple choice questions that you're going to have to spend like 2-3 minutes having a go at. But ideally you want to be able to make a good try at them within the first minute. Okay. Let's stop this poll. Show results. Okay. Not entirely sure. Okay, so option A in this case was the correct answer. Yeah, okay, it's kind of weird. I'm not entirely sure why it does that. Okay. Alrighty. Let's have a look at the working out. So the first thing I like to do when I start these questions is always define my two variables, right? So the first variable that I'm defining is orange, and they both follow a normal distribution. So I can define my variables first. Then I set up the sort of like my combined linear variable. So that's what this is. I find my expected variable, my expected outcome. So remember, mean is the same as your expected outcome. Okay, so you can quickly find out your expected outcome and you get 764. So from here, I can eliminate B, I can eliminate D and E. So I know it's between C and A. If you can get that done, and you still don't know how to solve the problem, that's fine, because you're down to 50% odds. That's pretty good odds. Ideally, you do want to know the answer, but if you can't work it out, and you're short on time, then that's fine to guess. Okay, the next thing we want to do is work out our variance. So since we have three separate O outcomes, we have to times our variance by 3 here. And since we have two separate L outcomes, we need to times our variance of L by 2. And so we chuck this into our formula, and we get the variance of x is 261. But we want standard deviation, so we need to take the square root. So the square root is 3 root 29, and our answer ends up as A. Hopefully everyone found that one okay. Okay, I'll start the poll on the next one. So deactivate poll. Okay. Let's run poll 2. Okay. I'll give you guys a minute to have a go at this. So 9:58, I think. Another thing I like to do when having a go at these questions is to highlight key pieces of information. So let me see if I can get my highlighter out. Okay, so we can see that the mean here is 200 grams. We have a standard deviation of 5. This is for the oranges. And the lemons have a mean mass of 70 and a standard deviation of 3 grams. Okay. So they're telling us that the fruits are normally distributed here. So they want the randomly selected orange will have at least 3 times the mass of a randomly selected lemon. Cool. So that's what our combined linear variable is going to look like. Okay. I'll give you guys 30 more seconds and then we'll go through the question here. Ideally, most of this is done in your calculator and your CAS as well. Just because in exam 2, we want to be using our CAS as much as we can, and yeah, utilizing it to its full ability, just to save us as much time as possible. Okay. Gonna lock voting and show the results. Okay. So people are split between B and C. Okay. So the correct answer for this one was C. All right, let's walk through why. So again, the first thing I'm going to do is define my variables. So, and the reason we do this, it's just a good habit to get into. So when you do your short answer question, by defining your variables like this, you make it, you collect all this information in this entire line into just one quick little bit of information, right? And so you can just keep glancing up at that if you forget what your mean and your standard deviation is. It also makes it very clear to the examiner what you're doing. Obviously, that doesn't matter too much in multiple choice, but yeah, I just think it's good to have there for clarity. So then your examiner isn't guessing what O is and what L is. They probably know, but just for the sake of clarity, or if you're using weird variables, yeah. Okay. So we defined that, And so then now I want to create my probability set, right? So we want to know that the probability that a randomly selected orange, so O, will have at least 3 times the mass of a randomly selected lemon. So I'm saying that the probability that O is greater than or equal to 3L. So that means that. So then I want to rearrange this. So this is greater than or equal to 0. And so I can create my own new random variable. X is equal to O minus 3L. And that's my combined variable. So next thing we need to quickly do is work out our expected outcome. So expected of O minus 3 times the expected of L, because that 3L is out there. And that's going to give us negative 10. In this case, so this is basically the opposite of what we did earlier. So this is when we multiply by a factor of something, right? So that's where the 3 comes from. So when we chuck this into our variance, 3 is going to be squared. So we get 9 times the variance of L, which gives us 106. And obviously take the square root of this to find your standard deviation. So then in your CAS, under normal distribution, so CDF norm, I think, on the TI and SPILE, you can just chuck this in and it should spit out your answer. When you want to do it for Z is greater than O, and that gives us option C. Cool, hopefully that made sense with everyone. All right, so in most cases, so let's start talking about the sample distribution. In most cases, we generally look at one sample, and you can see that this is our sort of formula for it, for the normal distribution. Anyways, this is what it looks like. So a sample distribution is if we take a sample of some random size, and then we calculate the mean of that sample, and then repeat it for like the same number of times that size was. And this gives us X bar. So this is known as X bar. And X bar is normally distributed with this formula here. So this is basically a summary of what I just said. So we take a sample of size n, and then we calculate the mean of that sample, and then we calculate that mean over a number of samples n. So what this gives us is the mean of a variety of different samples. It's the random probability of that a mean will be something of a certain population. So we call this the sample mean distribution. So you can see that our variance is given by the standard deviation squared over n. I'll write this down as well. So sigma squared over n. As we take n and we approach it to infinity, so if we do the limit of n approaches infinity, our variance is going to equal 0. Sorry. So as our sample size gets bigger, the more accurate our sample mean is to the population mean, right? But yeah, so that's basically it for this part. So the population mean will be given by mu, right? So that's the population mean there. So as n approaches infinity, this approaches 0. So this is going to approach 0. And so when that happens, our X bar approaches our mu. Just get rid of all of that so it's easier to see. Okay. All right, here's another question. I'll start the poll for this. I'll deactivate the poll now. This should be poll 3. Okay, have a go at this. I'll give you guys, again for this, I'll give you guys a minute. So until 10:06. Again, I'm just going to highlight some key pieces of information. So we have petrol consumption, and is normally distributed. I actually don't know why I highlighted that bit. That is not really important. Okay, so it's normally distributed. We have a mean of 12, and we have a standard deviation of 2. So they want to know that the probability that the average petrol consumption of 16 cars exceeds 13. Cool. So I'll give you guys a couple more seconds and then we'll work through our solution. Okay. Hopefully that was enough time. So show results. So we've got one person who's gone for C and another person who's gone for D. Alrighty, I'm going to reveal the answer. Actually, I'll reveal the answer at the very end. So again, the first thing we're going to do is assemble our random sort of like variable. So we need to define our random variable. So we're defining x as, so this is for the population. So keep in mind that this is not x bar, but for this one, we need to find x bar, right? Because it's average. So this sort of implies x bar. Get my laser pointer back. Alrighty. So we assemble our random variable of x here. And so we see from here that our n is going to be equal to 16. And then we use this to assemble our probability statement. So we want the probability of the sample mean distribution to be greater than 13. So we needed to build our sample mean distribution. So the expected of x bar is just the same as the mean. Standard deviation is just going to be standard deviation of x over 2. So it's going to be 2 in this case over 4, and that gives us 1 over 2. And this is our sample mean distribution. And so we now chuck this into our calculator, and we get option C. Alrighty, so sure correct answer. It was C. So well done to everyone who got C. I'm going to deactivate that. Cool. Okay. Also, one thing to note, so every time you guys do get a question wrong, write down what went wrong. Was it, that you didn't understand the concept well enough? Was it a simple arithmetic mistake? Was it a simple calculator mistake? And you really, between now and the exam, you really want to hone in on those tiny errors that you're making and try perfect them to the best that you can, right? Yeah, we really want to use this time leading up to the exam to perfect our little simple mistakes and try, get as close to perfect as we can, I guess. Okay. So let's talk a little bit about the central limit theorem. So basically this says, this says that any distribution, as n gets larger, our random distribution approaches n. So you guys generally use this in special methods for the binomial distribution. So when n is greater than 30 for the binomial distribution, you can just approximate it as a normal distribution. But this also applies to a variety of different distributions that you'll learn later on if you do take statistics. So things like a Poisson distribution or a chi-square distribution, they all follow the same rule. As n increases, they all still approach. As I was going to say, yeah, that didn't make sense. Sorry. So as your sample size increases, they're all going to approach the normal distribution. Okie dokie. For special methods, we can use it for n is greater than or equal to 30. And you need to calculate the mean and standard deviation first, and then you can put that into your sampling formula. All right. Also note that you're using a different sort of sigma there. All right. So when we have a large sample from a large population, we can approximate our sampling distribution, so our x bar, to be normal. But yeah, so we need to be able to use large population size to approximate that central limit theorem. And that's sort of the giveaway in the question, right? They'll say this was taken from from the Australian population or whatever. And using that, you can sort of, since the Australian population is incredibly large, you can use that to recognize central limit theorem and then apply your central limit theorem formula instead. So we need to have methods of determining our standard deviation and mean. So there are proofs in your textbooks, and I'm not going to go through the proofs here. A cool exercise for you guys might be to have a crack at the proofs yourself. So yeah, I think that was a pretty fun thing to do. I think our teacher maybe made us do that when I was in year 12, but yeah. Okay, so your mean is just going to be equal to your probability. By the way, so this is all from the binomial distribution. That's where this has been pulled from, effectively. This is known as a standard error as well. So sometimes you're going to be asked to calculate the standard error. That's just the same as the standard deviation, but just for a sampling mean. Okay. Okay. Cool, sorry. So when we apply this to the binomial distribution, we need to recognize that a binomial needs n independent trials with a set probability of p, right? So that probability of every single trial occurring needs to be the same. So when we have, sorry. So we need to have n large enough, and we need to have p sort of not as like a determined sort of thing, right? Because what I mean by like a determined value is that if it's close to 0, then the outcome is sort of determined. And if it's close to 1, it's also sort of determined. It just needs to be somewhere in between. So not at 0% or at 100%. And we sort of just keep increasing the value of n. Our distribution will sort of approximate to looking something like a normal distribution. So then we can say that the binomial mean, if you guys remember this, the expected value of the binomial distribution. I'll just quickly write this out. So e of x of a binomial distribution is n comma p. And I'm not going to bother writing out the standard deviation because it's already written here. But yeah, so we just use the binomial values and we just sub that into a normal distribution equation. These conditions do need to be met. So this sort of is like a mathematical way of knowing when this is held. So we need to always check our conditions. So before we apply the normal approximation, check your n times p, check that it's greater than 5, and then check this as well. And all that does is make sure that it's not close to 0 or 1. Okay. Here's a question. I think it's got to do with a random variable. Have a go at this. I'll start the poll. I'll give you guys a minute to do this. So I think this is poll 4. Okay, cool. Have a crack at this. I'll give you guys until 10:15. In the meantime, I'll start highlighting some key bits of information. So we're dealing with a probability density function, and that's given by this. We have a large number of samples, each of size 100. Okay, so this is well above 30. The distribution of the sample mean will be approximately normal, so they're telling us that. They've told us the mean, which is quite nice of them. And so all we need to work out here is our standard deviation. Okay. Alrighty. I'll give you guys a couple more seconds, and then we'll start walking through this. So some of the key bits that you guys want to be using in this is our formula from here and our formula from here. So it's primarily this formulas that we're concerned with here. Okay, let's see how y'all went. So, show results. Okay, so one person went for A, one person went for B. Let's work through this. So, first bit is identify that your sample size is 100. So this is well over 30, right? So you can use your normal, like your central limit theorem. Central limit theorem does apply here. So first thing I'm going to do is my standard deviation of x bar is the standard deviation of x over square root n. So that's all I've got to work out here. So we need to sort of figure out our standard deviation of x from this bit there, right? So if you guys remember with probability density functions covered in methods, you have your integrand equation. I think this was in the summary book, like the summary bit a little bit earlier. I think we'll scroll. Actually, I'm not going to go all the way back to that. It's going to take me forever. All right, so we just chuck that into our variance formula, and this is what we get. And then we take the square root of that, which is root 2 over 6. And we can chuck this into our formula, and we now end up with option A. Cool. So well done to everyone who got that one right. Show correct answer. Okay, I'm going to deactivate this poll. So the other common option was option E. So it was split between A and E. So I think with E, it was just like an error with working out your variance and then taking the square root of it here. Okay, cool. But yeah, E looks pretty similar to that. So I think the only error that could be made was with the denominator of your standard deviation there, if we were to get E instead of A. Alrighty. So our next topic is confidence intervals. You guys would have covered this in methods as well. And we'll quickly talk about what a confidence interval actually means. So I've left these blank so you can sort of fill that out. Well, I mean, it's like an unknown. So this is like a general term, right? So with a confidence interval, we can say with some percentage certainty that the population proportion falls between two different areas. So if I've got my, my sample trials and I'm setting my bounds between, I don't know, like 5 and 10, and I want to do like a 95% confidence interval, I can say that within 95% certainty that my bound, like my mean sits within these two bounds. Right. All right, so this is a bit of a written example. So if we have 100 samples and I do a 95 confidence interval for each of these 100 samples, 95 intervals that I find will actually contain the population proportion, while 5 of them won't. Another thing to have a look is that the more certain we are that our confidence interval, the more certain that our mean will fall in our interval, the less useful it becomes, right? Because so the more certain being us increasing that percentage value, like, instead of 95, let's say I do 99%, because there are more possible values. So what ends up happening is, so let's say that this is the width that I look at for a 95% confidence interval. 95. If I look at a 99%, all I'm doing, it's not only like, it's a bit weird, but it's just like sort of increasing that width of my confidence interval, right? And so I will have more pieces of data that fall into that percentage area, but it won't be as accurate anymore, right? Because now I can have my mean from anywhere from here to this bit instead of between like some narrow limit. So hopefully that makes sense. We'll also talk a little bit about the maths as to where that comes from, and it has to do with our k value here. I should have mentioned this here is a pretty important equation. Cool. So this bit here, that's a pretty important equation. That is our confidence interval equation. Sorry. But yeah, cool. Oh, that's not good. Less water. Cool. So this is our confidence interval equation. It's just a condensed version of this. So each sample will have its associated confidence interval, right? And this bit here is known as the margin of error. So you would have seen this in in methods probability. This is the one that you'll be using for X bar. So you'll use this for proportions. But when we're using sample means, we use this formula, right? Okay. If you guys remember from methods, this is just simply known as the margin of error, which is where that m bit comes from. Okay. So the sample standard deviation is always approximated to the population standard deviation when we run these. All right. I think it's pretty cool to have these values memorized. Simply, like, I'll run through the calculations to work out the various confidence bits. I'd say have this in your summary book as well, so just this bit here, just because it'll make it a little bit easier to work out our values when we get these in a question. So these are the most common ones. We get 90%, 95%, or 99%. You can see as we increase our degree of confidence, our margin of error increases. So this bit, that there, is going to increase. So our margin of error increases, and then the width of our confidence interval increases as well. Okay, so this is 20 different samples, and all their values, so let's say, I don't know, this is like from 1 to 100 something, all those different values are like lined up there, right? And these are the confidence intervals that we've run. So this is like the bound A and this is the bound B. So with a 95 confidence interval, that indicates 19 out of the 20 samples. So all of these samples contain the mean. But this one here, its confidence interval doesn't lie within the mean. So that's what the 95% bit sort of talks about. Alrighty. But yeah, it is a good idea to memorize this. Also, yeah, an integer multiple of the standard deviation, that's important to know as well. So integer multiple of standard deviation, we need to know that 95% is 2 standard deviations. Okay. This is the calculation that we run through to work out our k values. So we do need to use our inverse norm. It's probably easier to not chuck all of this into one formula straight away. Work this out in separate different parts. So this is just saying if we're using a 95%, you're going to have to do 95 over 100. So just convert your percentage to a decimal value when you do these. And then all we're doing here is manipulating our normal distribution. So if you guys remember symmetry values, that's all we're doing here. And all we do is rearrange and then chuck it into inverse norm. So inverse norm should be a function on your CAS. That's different from, from Mathematica to ClassPad to TI Inspire. So I think Google would be your best friend to work out where this is. All right. I probably won't give you guys the time to have a crack at this. Maybe I'll give you a minute or two to have a read. Maybe start your working out. If you can finish, that's pretty cool. I won't be running a poll, but just for the sake, just so that we can get through most of the content, I'll probably only give you guys like a minute or so to have a go at this. Realistically, in your exam, you'd have about 3-ish minutes to have a go with this. Is 1 mark per minute. But yeah. I'll also point this out. So when I brought up the integer multiple bit, that's what in exam 1, that's usually what it uses. So the integer multiple, so for 95% it would be 2, for 99% it would be like 3, for 90% it would also be 2. And so we'd want to use 2 here. Okay. Hopefully you guys have read the question, identified some of the key bits, and so now I'm just going to quickly run through its solution. Okay, so first thing I want to note is that my it's telling me that my variance is 16, so my standard deviation is going to be 4. All right. Then I can use this to work out my sample mean, right? So x bar. So the lowercase means that this is a particular outcome. And the capital letters mean that that's the random variable. This is a particular outcome. So I can just use this to quickly work it out. So total mass of this, so then I can work out its mean mass, which is 105. And I can use, and that tells me what my n value is going to be. And from the table beforehand, I can work out what k is, and then using the integer multiple bit, I know it's 2. All right, so first thing I always like to do is write out my formula. This might be in your formula sheet. I can't remember. Hopefully it is. But writing it out just makes it clear to you what the formula is, and it also makes it clear to your examiner which formula you're using. So if you do make a mistake somewhere else down the line, maybe they're kind enough to have a look at this and give you some consequential marks. All right, so now I'm going to just chuck everything into my equation here. And that spits out like this. So this is a bit painful to do in an exam 1. You're just going to have some good techniques to work this out. So 4 over 25, that's going to be 4 over 5, so 0.8. So 2 times 4 over 5 is just, yeah, that's just going to be 8 over 5. And then you're going to use the 0.2s to work out what that actually is. So using 1 over 5 is equal to 0.2, you can sort of simplify that down, and then you'll end up with these. Okay, cool. All right, so we've gotten through the first bit of statistics. We are kind of behind schedule, but hopefully that's okay. I'll probably just take a little bit of time later away, but I do want to get through statistics. Okay, so the reason that it's the easiest question is because it's almost always the same question, just in different values every single year. What we're testing with a hypothesis test, we're testing like the validity of some statement based on a sample trial or a set of sample trials. Right. So for example, this one is talking about a medical treatment to decrease the mean. To decrease the mean population size of a virus. And so using a sample, we can test if this claim is true or not. So hypothesis testing has a lot of real world applications. We use it quite a bit in research. We use it a lot in drug testing and drug design. So yeah, I think it's really useful. And I think it's a pretty cool topic, really. But yeah, every year, almost always these same questions. Okay. It's also important to know that when we run our hypothesis test, we're using a sample, right? So we're going to be using sample standard deviation and not population standard deviation. So yeah, don't mix up the two. It's pretty easy because all they differ by is a square root n. So it's good to know the difference. So we're using a sample here. So in hypothesis testing, we're using the sample to make a generalized statement about the change in a population. But yeah, just remember which one to use and try not to mix up the two. Okay, so when we do a hypothesis test, there are some like rigid rules that we sort of need to follow and some rigid statements that we need to write down. So the first thing we need to do is to set up our statistical hypothesis. So we assume the rule that something is not guilty until proven. So our first hypothesis is known as the null hypothesis. So null as in that there's been no effect, that the treatment is ineffective. And we write this down as H naught. So we say that H naught, so you always have to write this down. This is always the correct statement. So H naught, you write that the mu is equal to the mu before. So yeah, this mu refers to the new mu. And you'll just, so like, let's say it says that the initial population's mean is 130, and the sample's mean is like 140, right? You would still use mu before, so 130, you'd put that there. Okay. The alternative hypothesis is the effect, right? Is the effect you're testing. So it might be desired or you might be against it. It just shows that whatever has been done has changed the population mean, or the like sample mean, hence the population mean. Okay, so it doesn't always have to be like greater than. We have three possibilities for our alternative hypothesis, or H1. These two are known as one-tailed tests, and this is known as a two-tailed test. With one-tailed tests, the difference is that they are directional, right? So here we're saying that the new population mean is greater than the old population mean, right? Whereas in this one, we're saying that the new population mean is less than the old population mean. Whereas with the two-tailed test, it's non-directional. All we're saying is that that the mean of the population has changed. That's the only statement being made there. All right, the next thing we want to do is set up a significance level. So you guys would have seen this. This is the alpha value. So we need to say that our result is statistically significant, and that's what the significance means. The default value that they usually set is 0.05, but sometimes they'll change that just to throw you guys off. Sometimes they'll also use like a percentage. So what this is, right, is that it says that, we can say that there's less than a 5% chance of getting two heads. So this is a coin example. Okay, so that's the coin example here. All right, the p-value is what we're actually calculating. It's the probability of getting an extreme value, assuming the null hypothesis is correct. So if I write this out, so p is equal to probability of an extreme value. An extreme value is anything that's not expected. So extreme, let's write E here. That's gonna be really annoying to write out, sorry. Given that if the null is correct, that just means the mean has not changed. Before. Okay, sorry about that. It's kind of annoying, but oh well. Okay, cool. So when we do our p-value tests, they always need to, so we run our p-value test, we get our p-value, then we need to make a determination using our significance value or significance level. All right. So let's say we're using that virus example from before. The size of the virus will decrease after receiving treatment X. So my my H naught will be that mu now is equal to mu before. And my H1, my alternative hypothesis, is just saying that the old mu is going to be less, the new mu is going to be less than the old mu. Okay, cool. So the p-value is given by the probability, in this case, of x bar is less than the sample mean, given that the population mean has stayed the same. Replace the sign depending on which test we're doing. So I'll just show you the other possible signs. So if the test is the other direction, you want to use this, or if it's a two-tailed test, you want to be using this one here. So just replace that sign. Okay, so to calculate the p-value, we have three different ways that we can do it, and three different ways we can chuck it into our calculator. I just tend to use this method, the method 2, the norm CDF one, like this one here. I just think it saves time, so I don't need to work out my standard one there. But again, this is personal preference. That's just the one that I've been used to using, so that's the one that I just stuck with. Again, if you want to know where these are on your CAS, your best bet is to Google it because everyone's using a different CAS. So yeah, cool. All right. So the last bit of a hypothesis test is we want to work out our p-value. So I've shown you guys how to work out the p-value for a one-tailed test, but what about a two-tailed test? With a two-tailed test, remember the new mean is not equal to the old mean, right? So we're just looking at half of the alpha for one side. So we have no direction. I think a diagram sort of pops up. There you go. I was going to draw that in, then I realized I already had this in. So we want to know that the mean is less than or some value or greater than some value. So we have two extremes that we're testing. So all I really need to do is work out the probability of this area and then double it, right? Because of symmetry properties. So this is where the 2 comes from. So the probability of a two-tailed is just 2 times the probability of a one-tailed test. We're using the same values, right? So that's all this formula is. So you just chuck your things into this formula and yeah, cool. And you should get your answer for a two-tailed test. All right, so we need to be able to make inferences from our calculations, right? So we need to be able to use alpha to do this. So if the p-value is greater than alpha, then we don't have enough evidence to reject h0. So we have to say, so insufficient evidence to say that the new mean is different from the old mean. But if it's below alpha, then you have to say any one of these statements. And you have to make these statements as well. So use this exact wording, I'd say, because they're pretty picky on the wording, just because it's a very like convention sort of thing. So if our p-value is below alpha, then we have pretty good evidence to support, to reject the h0 and support the fact that the new mean is different from the old mean. Okay, cool. Hopefully that's good with everyone. Every sort of set of wording is aligned with a different sort of p-value. So the lower the p-value, the stronger our evidence. Okay, so this is just a quick summary. But yeah, that was just a quick summary of hypothesis testing. So, okay, so we know that there are going to be some errors, right? There's always a tiny chance the p-value is wrong, and that's just due to some random sample distributions. So in hypothesis testing, there are 2 main types of errors. So our first error is when we reject h0 when h0 is true. So this is known as a type 1 error. So this is a false positive. And our second error is when we don't reject h0, even though the h0 is false. So this means that the mean has changed and we fail to recognize that the mean has changed. This is known as a type 2 error. Cool. So I'd say chuck this table down in your notes. This sometimes is usually asked as like a definitional multiple choice thing, but every now and then they do get you guys to calculate probabilities with this. You're probably not going to need this for the exam, hopefully, but I did have this in my exam last year. All right. So with type 1, what you're doing is you're rejecting h0 below alpha, even though you shouldn't have. So you can reduce type 1 error by decreasing your significance level. But when we decrease our significance level, we're increasing the chance of a type 2 error. So to work out the chance of a type 2 error, we set our p-value at whatever the significance level is. So we say p-value is equal to significance. So in some cases that always, that might not be 0.5. And what we're doing is we're just setting our p-value to like the borderline value of acceptable. Okay. And then you just want to use this and solve for x. All right. So type 2 errors decrease with sample size. And when we want to work out our type 2 errors is we want to find the value when type 1 meets type 2. So this is the probability of accept h0 given that h0 is false. And that is that sort of like intersection period. So with errors, right? So this is from your study design. Students should be able to identify the nature of an error indicated in a hypothesis test context. So like in a context, you want to be able to apply this table. This is effectively what they're saying. And you should be able to interpret type 1 and type 2 errors. Most of the time, you're not asked to calculate the probability of the error directly. I think last year they were they just kept like pushing you in the right direction to calculate a type 2 error. But you're never like actually asked to calculate it. Though in my SAC for school, they did get us to calculate it. So, alrighty, cool, nice. This is a question from VCA 2017. I'll give you guys a couple seconds to read through it and then we'll work through it together. All right, So the first bit again is to highlight the key bits of information. So we have a normally distributed random variable, and that is the bank claims. It has a mean of 400,000 and a standard deviation of 30,000. So an organization believes that the average loan amount is higher than the bank claims. All right, so this is a one-tailed test. So to check this, the consumer organization takes a random sample of 25 loans. So this is our n value, and it finds our sample mean, lowercase x bar, to be 412. Okay, so this is what's just done. It's basically boxing everything that we've just boxed. So this is the direction of the test. So this is our H1. Okay, cool. So your first statement is always H0. So mu is equal to 400,000. And our H1 is that mu is greater than 400,000. All right. So that would be 1 mark for that. Pretty simple, right? All you had to do is all you had to do was identify what your null hypothesis and alternative hypothesis was. Okay. Next, we need to write down our expression. So that's 1 mark here for writing this down. And then all we have to do is chuck this into our formula. So I wouldn't say, I'd say don't write this down. This is just what you're writing into your CAS, right? And you get your p-value here. Keep in mind they only wanted it to 4 decimal places. So with most exam 2's probability questions, they tend to want it to 4 decimal places. But it's good to always double check because sometimes they'll trim it up. They'll change it to 2 just to make the student stumble there. Okay, so our p-value is 0.0228. So at a 5% level of significance, that's an alpha of a 0.05. So our p-value is less than alpha. So this means we reject the null hypothesis, which is the bank's claim. So the bank's claim should be rejected, is what we're saying. Okay, so they want the largest value of the sample mean that could be observed before the bank's claim was rejected at a 5% significance level. So they want the answer to the nearest $10. So we want a p-value of 0.05, right? That's all it's really asking here. So we set up our equation like this, and we run an inverse norm for this, effectively. And this is our sample mean, effectively. So remember, we're running inverse norm. That's an operation on your CAS. And that's what we're really doing here. So when we run our inverse norm on this, we'll get 1.644. We equal that to this, and then we reshuffle and we solve. Okay, so that is our content block 1 complete. So now we'll just be going into our little break. So ATAR Notes primarily offers a bunch of free resources, but recently they've also started expanding into TuteSmart, which is their sort of private sort of tutoring sort of organization thing. We do have a revision pass for $379. So these are live classes that happen weekly. You'll get all current classes in the future, access to all of those, and all of the previous recordings and all the resources as well. And I think this is for all of your Year 12 subjects. So check this out if you're interested. But yeah, that's just something that I think that's cool that they offer. All right. So we also do some one-on-one tutoring. I personally tutor mainly methods, bio, chem, and that sort of stuff. But yeah, so go to this link, book an info call. David will basically match you up with someone based on your needs. But yeah, cool. All right, so let's have a little bit of a break. I'll give you guys about 5 minutes, and then we'll come back and we'll sort of go through a bit of the questions. I'll have a look if anyone has asked any questions. Okay. If you guys have any questions, just submit it through Slido on this. Um, it should pop up, hopefully. Here. But yeah. Okay. Something else that I'm just gonna have to shout out is Ed Unlimited. So Ed Unlimited, it's like an online sort of guide, sort of like a study guide library. We have a bunch of neat stuff, practice exams, all the ATAR notes practice exams, all of the ATAR notes guides as well. Um, if you guys do want to have a like check it out. Um, you can use my code Major VCE, so it'll be free for 21 days, which I think is pretty close. Like it goes right up until your exams, basically. So you don't really have anything to lose. So I definitely do check it out. I think I used it towards the end, so I did use a lot of like the NEEP resources towards the end of my exam period. I think they were pretty good, especially for bio and chem. Okay, I'll just leave that up as well for a bit. Okay, we'll get started at 10:48. So, okay, let's get started. Okay, so yeah, so with content block 2, we're just going to go over complex numbers. I'm going to have to skip over some stuff just for time, but all those notes are there, they're in full detail. Yeah, so all of that there is just for you guys to use for your notes. So I'm not going to cover how to draw reciprocal or inverse trig graphs, but I will talk about like domains and ranges of second functions. I think complex numbers and calculus are the main topics that I really want to cover, simply because they're just quite important. Okay, so let's start with complex numbers. So the first bit of complex numbers is knowing how to convert things to polar form, right? So it's just the way that the complex numbers use our Cartesian plane system. So we need to be able to convert between Cartesian coordinates, which is this, and polar form. So if we want to go from Cartesian to polar form, we have to figure out everything in this form as well, right? So our R is just the magnitude. So hopefully I can draw out like a pretty good diagram of what this looks like. So let's say we have some complex number, Z here, right? So that's Z. R is like that magnitude bit, and theta is that angle made there. Okay. This x-axis component, let's see if I can use a different color for this. Here's green. So the y-axis component is going to be this part of our Cartesian system, and the x-axis component is just the x bit from our Cartesian equation there. Okay, so to figure out r, which is just the length from 0 to z, we just need to use Pythagoras theorem. So x squared plus y squared, and the square root of that gives us r. All right, cool. And to work out theta, we just use tan theta is equal to y over x. And then we take arctan, and so then theta can be calculated through there. All right, so when we work out our polar form angle, so yeah, this is just the diagram that I just drew. When we work out our polar form angle, it's super important to give our domain. So the arg, or the argument, so this is known as the argument of the complex number, has a set domain. So the argument is like that theta bit. So the argument is always from negative pi to pi, not inclusive of the negative pi. So you do have to do those quadrants and then map out which bits are positive and negative, and you have to use that to work out your arctan. So everything that you do in methods to work out the arctan value, you have to do it here, and you have to make sure that it all fits into these quadrants. Okay. Hopefully that made sense. If not, just chuck up the question. I could chuck a question up on slide. All right. So when we multiply and divide things through polar form, we have a couple rules, right? Also, when we're doing multiply or dividing, we always use polar form. So whenever we multiply or divide a complex number, I definitely say always use polar form because it's just a lot easier. Yeah, see, use polar for this, as said in the notes. So when we multiply things, we just times the two r values together and we add the angles. When we divide the r values and we simply just subtract the angles. Also, when we work out conjugate, it's just negative theta. So if you guys remember, if x plus, so in Cartesian form, that looks something like this. So x plus iy, if that's z, then the conjugate of z, so z bar, is just x minus I y. Okay, cool. Anyways, so this bit here is just saying that we add the angles. Okay. Also, note the difference between the conjugate and the reciprocal. So the reciprocal is just 1 over z. So all we're doing is the polar form of 1 divided by r cis theta. If you go on and work out the polar form of 1, you will just simply get 1 cis 0. And that's where the negative theta comes from. Okay, this is like not fun to write. Okay, cool. Managed to get there in the end. So yeah, we just convert this to polar form and then we simplify, and that's where we get our reciprocal bit. Okay, so De Moivre's theorem. So when we have, so some numbers can have 2 square roots, 3 cube roots, etc. We use De Moivre's theorem to find the nth root of a complex number. So there are n solutions for n roots around a circle. So you can go around the circle n number of times depending on the number of solutions we're looking for. So when we work out polar form, we always want everything to be, when we work out De Moivre's theorem, we want things to be in polar form, and we want everything to fit into our argument of theta. We want our theta to fit in that domain. Okay. So for example, if we have 3 roots, you'd be subbing in things like z is equal to 0, z is equal to 1, z is equal to 2, and you'd get 3 different values. 4 roots, you'd go 4 times around the circle. 5 roots, you could go 5 times around the circle, and so on. Okay, so when we solve for De Moivre's, we need to equate r variables and theta variables. So these are the steps that I sort of applied when I used De Moivre's theorem. So first thing we do is write out our formula, and then we convert our complex number into polar form. Just to make it a little bit harder, they always like to give the complex number to you in like a Cartesian form. So always convert it to polar form. So r of n is equal to the magnitude and n of theta is equal to the argument. So when we find our angles, just find one angle and then use like the 2 pi bit to add the angles equally apart, or like some like 2 pi n to add angles equally apart. Cool. So always make sure that your domain is met. So negative pi to pi inclusive. And then at the end, convert to Cartesian if you need to. Okay. So I think we have a practice question with de Moivre's soon. All right. So if all coefficients, so when we use conjugate root theorem, it's just a very quick hack to solve polynomials. So it only applies if all of our coefficients are real. So for example, if A, B, C, and D are all real, then conjugate root theorem applies. So all it says is that if x plus yi is a solution, then we have the conjugate as a solution as well. I don't think I have time to go through this today, but I do have the answer. Well, I think I did have the answer though. Yeah. So what we can do is, given that z minus 2 is a solution, another solution we have is z plus 2. So we can sort of write out a bit here. So like z minus 2 times z plus 2. And we can have z plus a. And what you want to do is you want to equate this to all of this bit here. And then you want to resolve for a. And so that's how we can use conjugate root theorem to make solving these questions easier. Okay. So these are on your formula sheet. I'd say try and memorize these to your best of your ability. Otherwise, you're going to be flipping through your formula sheet during the exam, which is just, using up valuable time. So we need it when we have trig with weird angles. So we have, like if we've got something like 3 pi over 8, that's a weird angle. You'd be using one of these formulas to simplify that, probably one of the addition formulas. Okay. Yeah. Also, there are half angle formulas. So with half angle formulas, all you have to do is replace the half. So you just want to replace the 2. You just want to replace that with 1/2 x. And then you want to resolve that though. And then you'll get a different formula, but that's how we sort of work it out. All right, let's talk a little bit about our trig function. So when we have some function, so let's talk about arcsine function here. The first thing we want to do is try work out our domain, right? So I won't go through this in too much detail, but when we work out the domain, what we want to do is basically reverse the transformations that we've applied to x, right? So we know that with arcsine, we go from -1 to 1, and this is in your data book or formula sheet. So we want to, so these are all the transformations applied to x though, right? Get rid of that though. Okay, so these are all the transformations that we've applied to x. And all we want to do is add in c and then divide by b. And this is our new domain. But with the range, we want to start with our altered bit. So what we want to do is we want to subtract d to this side and then divide by a. So we get y minus d over a. And then all we have to do is reverse this transformation again in this manner. So these two, I'd recommend having these in your formula book or your notebook when you take into exam 2, and know how to solve these in exam 1 as well. Cool. Let's talk a little bit about differentiation. So I recommend have this in your data book as well. It's just memorizing formula. So with this thing here, this is one of those quick derivatives that you can memorize, right? So if you do have any other quick derivatives that you want to memorize, try memorize it. So this one, all you have to do, because it's x to the power 1/2, that's all we're doing here. We're just moving the 1/2 to the front, and then we're subtracting 1. So that's how we get this. In your summary book, I'd say have a bunch of questions that you keep getting wrong again, or like differentiation bits that you always keep getting wrong. Have those in your summary book. So if they do ever come up in your exam, you can just flip to that page and have a rough idea of where to start. Okay. I'll just quickly check if we have some questions on the Slido. No, we don't. Cool. All right. So with our differentiation summary book, you want to also add these in. So these are some of the most useful ones, I think, that aren't on the formula sheet. So chain rule, it works in layers. This one's not in your formula sheet. I think you have the normal like du dx one. I'd say add this to your formula sheet as well. Simply because this is good for multiple choice questions. Sometimes they'll get you to work out like a general multiple choice question. So as in they'll give you like some general function g of x, some general function f of x. So then you'll need to work this out. One thing I noticed is that this bracket here is not closed. That's another thing you always want to do. Make sure all the brackets are closed. It's a notation thing and it's a convention thing, but sometimes they do care quite a bit and they can mark you down for that sort of stuff. Cool. So have these in your data book, your summary book, because they're not in your formula sheet. So things like this, that's not in your formula sheet. It just makes it easier. If you get something similar, you can just skip the thinking and you can just write it in here when you know it's correct. I'd say memorize this as well. This is quite important, that one though. It's pretty useful. And when we run these ones here, especially when we do our differentiations, be wary of your domains, right? So define your domain at the end if you do this. Okay. With implicit differentiation, this sort of becomes like muscle memory. When you see y, we do have an implicit differentiation question later on, I think. So we'll be doing that. But when you see y, just put dy dx straight after it. Make that muscle memory between now and your exam. Because I think this is the most common mistake people make, forgetting to put that dy dx in implicit differentiation after a y. With inflection points and concavity. So remember that when the second derivative is positive, we're hitting a local minimum. When the second derivative is negative, we're hitting a local maximum. But with points of inflection, our second derivative is 0, but our first derivative is not 0. The point of inflection is the highest rate of change for our derivative function. And when we have a stationary point of inflection, which is what SPOY is, our double derivative is 0, and our gradient is also 0. Gradient of the original function. So yeah, sometimes they do get you guys to draw double derivative graphs or derivative graphs. You'd want to be using all of these rules here to help you with that. And related rates, definitely use chain rule. Chain rule is your biggest helper when it comes to related rates, simply because you're basically using two different rates and you're trying to relate them. But yeah, so all of this, chuck it in your summary book, I'd say. Okay, U subs, or substitution by let U. So in my book, I always wrote these down as U subs. And so that's when you substitute a part of your equation, you just let it as U. When it comes to U subs, it's more of like a bit of a trial and error sort of thing. Sometimes the sub that you use won't work, right? If you use the wrong sub, it's fine. Just try another sub. And eventually, with a lot of practice, you'll get pretty good at using the correct U sub. And it becomes a lot about just recognizing which one you're using. Okay. So always the more so this is like a pretty good rule, I think. Always the more complex something is, that's generally what you want to let U equals. All right. So with our steps, the first bit we want to do is let U equal some component that's part of your integral, right? Then we want to find du dx and sort of arrange dx in a way where we can sub it in to our equation, right? So then we want to sub u and du dx back into the original equation. So then we have to convert the terminals. So as in, if you've got like an integral from I'll just write it out. So if you have an integral, that's a horrible integral. So you have a and you have b here. You want to convert these terminals, right? So you want to do u of b, and you want to put that into there, and you want to do u of a, and put that into your. You want to put that into your terminal 2. And then what you do is that you run the integral in terms of u here, and then you want to sub your original value back and leave your integral in terms of x. Okay, trig integration. There are a few rules. So we have different cases. We have odd powers and even powers. Personally, I thought it was the hardest form of integration that they get you to do. But yeah, most people also find this quite challenging. I think a lot of people in my classes found this challenging too. So there's only 2 cases, right? We have any odd power, or we have all even powers. So when we have odd powers, we have a couple rules that we need to follow. We need to split the odd power, so there is a power of 1, or the loner. So in this case, we've split it into sine of x and sine 4 of x. So we have the odd power by itself, and we have 2 even powers. All right. Then you want to use your Pythagorean identity to convert the other even powers. So we can do this. So now these look quite similar. And all you have to do from here is use a u sub. So in this case, you get u is equal to cosine x. You guys remember, du dx is going to be equal to negative sine of x. And all we can do now is just sub this in to our actual equation here. Right, so this will go there, and that will go into there. And then we take the integral like normal. If we do have a tan of x, then convert that into sine of x over cosine of x. Only if it's odd though. So generally, it's easiest to do everything with sine of x and cosine of x when it comes to integrating stuff with trig. Okay, when we have all even powers, we want to try convert them into these forms here, right? So then we can have an odd power once we convert it into these forms here. See that there is an odd power. Okay, so you need to memorize these formulas. There's no way around it. It just makes life easier, right? You can go without memorizing these, but I'd say you have to memorize them just because it makes doing these integrations a lot more straightforward. Okay. So what you'll do is when you have an even power, you'll make this substitution, and then you do the normal odd power method of solving it. Alrighty. Hopefully that is a-okay with everyone. All right. Another common question type is integration by parts, or IBP. You're not required to know the integration by parts formula, but the idea is, right, they usually have part A, and you need to find the different, you need a diff equation, and then part B, it's integrate an equation, and then part C is usually figure out, rearrange your last couple answers to figure out what the question actually wants. So this is also known as integration by recognition. You have this in methods too, but later on you'll learn another technique in university known as integration by parts. But yeah, they're just making that whole integration by parts bit a bit easier for you guys by splitting it into multiple parts. Here's just a quick summary book for integration. With log, remember to include R modulus. If we want to, not have the modulus there, we need to be able to justify why one side of the logarithm isn't positive. So we need to be able to reject the negative half of the logarithm. So you need to make a statement for that. But that is probably going to take a little bit more time. So I'd suggest just leave the modulus there. And yeah, memorize these 3 in particular. But you can also have these in your summary book. Just for exam 1, just have these memorized here. Cool. I'll probably just skip over this. This is all for your summary book. But yeah. All right. One thing I did want to talk about is partial fractions. We'll need this for a question that we're about to do. But when we work out partial fractions, there's a couple ways of running it. Some people like to do a simultaneous equation. Some people do other methods. The method that I like to do is, so these are things that you're going to just have to memorize. So like these standard equations, memorize them. But when it comes to solving them, what I like to do is, so multiply, so these two are equal, right? So you want to multiply both sides by x minus m and x minus m. So what we'll end up with is, oh, that looks like a modulus. Okay, sorry. So we'll have x minus n here, plus x minus m, and that's going to be equal to ax plus b. Okay, cool. Once you have this equation set up with your partial fractions, what you can do is sub in, so you can say let x equal something like m. So let x equal m. I realize I have the equal sign in the wrong bit. So you want to say let x equals m, right? So what ends up happening is your b component entirely cancels out. You substitute this, and then you can solve in for a. And then you repeat the same thing with b. So hopefully that made it pretty clear on how to solve partial fractions. That's just the method I used. I found that I was fastest with that method. An alternative way of doing it is using simultaneous equations. Alrighty. Here's another formula that I recommend having in your summary book. And this is Newton's law of cooling. This is just something that you have to know. This is in the study design from memory. You need to know both the derivative form and the function form. So so that's the temperature of the surroundings, and this is a proportional constant. You're usually either told to calculate the proportional constant, or the proportional constant is given. So what it does, Newton's law of cooling, is so it relates the difference between the ambient temperature, or the temperature outside, or the temperature surrounding the thing of interest, and the actual temperature. So the differential equation relates the two, and the solved equation solves for one of them. Okay, but yeah, just memorize it unless you use first principles. If they say use first principles, then you need to start from here and then derive this, right? But if not, memorize this and then skip to it, right? But if they do want you to show the derivation step, then you're going to have to start from here. So yeah, hopefully that makes sense. Okay, another common question type with differential equations is the mixing problems. Let me just check if there are any questions up. Okay, I'm not entirely sure if this is a problem with Slido. Okay, I have to check that later. All right. Okay, so concentration mixing problems. So these are when you have a substance going into a tank and something flowing out of the tank at a mixed rate, right? So, mind blank. All right, oops. So we have Q as our outflow substance, so that's its mass. And sometimes Q is going to be equal to concentration. So this is pretty important to know here. That concentration is going to be mass over volume. That's the wrong one. I thought that was a highlighter. All right, So we want to know that concentration is always going to be equal to mass over volume. Okay. So sometimes Q is going to be concentration. Sometimes it's going to be the mass of a substance. Either way, the equation that we set up is always going to be the same. It's always going to be what goes in minus what comes out. And that's going to be our change in substance over change in time. Also, take note of the units that they use in the question. If they're using grams, put that in. If they're using seconds, use grams per seconds. You always want to have units for this part. Sometimes you won't have units because they don't give you enough information to figure out the units. But if they do, most of the times they do expect units. All right. So with our inflow, we're going to be using. So it's going to be so it's going to be the rate of change in. So what we'll be doing is so they'll usually give you enough information to work out the amount that goes in. So the flow in per time times the amount that goes in per concentration of flow. And so that gives us this equation. And then our outflow is going to be the total mass that's in there, plus our volume, plus how the volume changes, which is what that sort of accommodates for. All right, so what this just shows is that our units do cancel out in most cases here. And so this is what our outflow equation looks like. So all you do is you substat into there, and you substitute this into your outflow, and then you solve. Usually integrate, find an equation of Q from there. So if they don't give you initial conditions, or the initial concentration, don't use this formula to account for that. Later, when you take the integral, that's when we use plus C to account for this. Otherwise, this formula becomes too convoluted and too annoying to solve. It's just easier to put that into the plus C. All right. When our inflow is equal to our outflow, then there is no change in volume, right? But when our inflow isn't equal to our outflow, this changes our volume. So, yeah, okay. Also, this is a quick note. If you are adding no substance, then your inflow is 0. Because your inflow equation accounts for amount of substance here. So that amount is Q, that refers to Q. If you're just putting in water and you're just diluting your solution, then your amount of Q is equal to 0. So then your inflow ends up equaling 0. And so then you only have things coming out. Okay. So when we solve these, the first thing I always like to do is draw out my solution or draw out my situation. So I'll have a little drawing of a tank. I'll show in an arrow that's showing the inflow, and I'll show an arrow that's showing the outflow. I'll include things like the volume of the tank. So here, this is a little diagram. So the volume of the tank, which is going to be its capacity. I'll include units as well, and I'll define my outflow, inflow formulas, and I'll write that here as well. So I'll obviously replace inflow and outflow with my formulas. And then I'd set up my differential equation, which is going to be inflow minus outflow. And then I'd take the integral of this with respect to time. So I'd get Q as my subject. Just remember with these initial conditions, don't forget plus C. Okay, the next topic with differential equations is going to be slope fields. Slope fields is usually a pretty low yield topic, as in you'll only get this in multiple choice, really, in exam 2. Sometimes in exam 1, so earlier exam 1s from 2007-ish, they'd get you to draw out actual slope fields, but they don't usually get you to do those anymore. All right, so the steps with slope fields is you want to look for some of the patterns, right? So when you have positive gradients, negative gradients, zero gradients, or undefined gradients, and you want to look at your actual functions. So with multiple choice, what they'll do is they'll give you a slope field, and then they'll be like, so use this to work out what function is given, right? So you want to use things like when the gradient function is equal to 0, when the gradient function is positive, when it's negative, when it's undefined, and you want to use that to sort of figure out what the actual equation could have been. So yeah, we look at the question, we look at what our derivative is. If we want to find what the derivative function is, we look for turning points or asymptotes. If we want to find a y, we look at the implied curve. So it's not dy dx, so we don't draw, so we draw on the curve, which is what those dots are. That's the implied slope. And so when you draw that implied slope, you want every point to be perpendicular to that given like dotted lines. If that makes sense. But yeah, cool. So I'd say chuck this into your formula sheet as well, or your summary book. So when you have a slope field question in the multiple choice section generally, you can just flip to this page and know what things to quickly look for. Okay, Euler's method. So you have this in your formula sheet, but I think the way that they've written it in the formula sheet is quite like confusing. So I'd say definitely memorize this formula. You've got to memorize it. The biggest problem that people have, I think, with this question here is not keeping account of their previous x and y terms. So when you don't keep account of your previous x and y terms and you don't write everything out in a table, you'll get confused and then you'll end up repeating the same thing and then you'll stuff up your answer. So when it comes to organizing your working out for Euler's method, write out your formula and count how many steps before you sub into the formula. So figure out how many steps of Euler's formula you want. So to work out your steps, you want to look at the number of divisions until your final answer, basically. And use a table. So use like a table of x versus steps, or a table of y versus the number of steps. Okay, cool. Hopefully that does make sense. So with Euler's method, all we're doing really is we're approximating the actual function using our derivative function and substitute it in values. So we're making multiple linear lines, and we're basically trying to create our actual graph by mapping it out using small linear lines. Okay, this is just a little bit of a summary bit for our differential equations bit. Remember when we use growth and decay, we want to be using this equation here. I'm not going to go into this in too much detail. This is just our summary sheet, so I'll just quickly skip past it. So it's got things like Newton's law of cooling, concentration mixing problems. You can add all of this into your summary book. The CAS does have an Euler function. Again, this is different from the TI Inspire to Mathematica to ClassPad. So just Google this and figure out which one your calculator uses. I think this one here is for the TI Inspire, but I could be wrong. Okay, I'll give you guys a couple minutes to have a crack at this question. Give you guys 3 minutes to have a go. So we'll be back at 11:27. Have a crack at this. There won't be any poll for this. I've only got polls for the multiple choice bits, but yeah, have a crack, and yeah, see how you go. Meantime, I'll check if there's any questions. Okay, hopefully you guys were able to have a good crack at this. I just realized I was not sharing the screen that bit, but hopefully you had access to the slides for that. All right, we'll start give you guys 2 more minutes, and we'll start working through it. All right, so when I look at implicit differentiation questions, the first thing I tend to look for is points I can make mistake and where my dy's are going to sort of pop up. So since we've got our y here, that's probably the only place my dy is going to come up. And they want us to find some part of c, so a value of c, such as the curve is defined by and has a gradient of 2 where x is equal to 1. So hopefully you guys had a go at this. We'll just quickly run through it. All right, so the first bit is to, I think this is written like this just because it's easier to type it out, but this is just y, right? So here is our function, and then we take our derivative. So this is just dy dx times y. Hopefully all of this makes sense here. We're just using our derivative formulas from earlier, from the summary bit of differentiation, if you guys can remember that. So when e to the f of x is, when you take the diff of that, you'll get this. Okay, cool. Next, we need to rearrange. So all of this is just this. Okay, so remember after y, we have our dy dx. And then we sub in x is equal to 1 and dy dx is equal to 2. So that's what they've told us here. And then I figure out what y is equal to, right? So that's all being done though. Once I figure that out, I need to start working out what c is. So I substitute everything back into here. So x is equal to 1 and y is equal to 3 over 2 into here. And I basically run my equation and solve for c. Okay, so this is just the examiner's report. So the main problem here was errors with algebra. So my tip when it comes to working through algebraic problems and minimizing the number of algebraic mistakes you make is to write out every single step. So even redundant steps like this, or steps that might seem redundant, writing them out will really help you crack down on your own errors and really perfect your technique. Okay, here is a rate in, rate out, so mixing question. I'll give you guys 2 minutes to have a go at this, and then I'll quickly run through it. So some things to quickly note before having a go is some initial values, right? So this is an initial condition here, dissolved in 100 liters of water. So we might have to use concentration here. Yeah, so they're using concentration here. So this is our inflow here. We can use this to work out our inflow. And this is our outflow. So the first bit is just us creating our expression here. And the second one is solving a differential equation. Alrighty. Hopefully that was enough time to have a go at this question here. I'm giving you guys less time than usual. You would have at least 3 minutes to do this question. I'm just, yeah, trying to cut down on time and make it a little bit more challenging for you guys. Okay, so the first thing we want to do, so then we want an expression of concentration, right? So the first thing to do is write down what concentration actually is. It's just mass over the volume at a certain time. Okay, so our mass is given by Y. They've told us this, Y kilograms. And we just need to figure out the volume at some time t. So 20 liters goes in, so that's the 20 liters, and 10 liters is always coming out. So my change is 20 minus 10 times t. So my total volume at all times is 100 plus 10t. Cool, so I've set up my concentration equation. All right, so they want us to show that the differential equation is related like this. So they want us to set up our differential equation. So remember with rate in, rate out questions, the equation that we want to use is inflow minus outflow is equal to dy dt. So when we work out inflow and outflow, we want to work those out separately, right? So inflow, this is the amount of inflow that's going in, and this is the rate that it's going in at. So it's 1/3 kilograms per minute. So I just multiply these two. My outflow, they're telling us that y is the amount that's going out, and we've already sort of worked that out earlier. And here's the rate that it flows out at, and you multiply this through, and we get this as our equation. Cool. So then all we need to do is set up our inflow, outflow, sub everything back in, and then rearrange, and we would have gotten the marks for the question. Nice. Alrighty. Here's a multiple choice question. I'll get you guys to have a go at this. I'll start the poll for it. I think it's this one here. Okay, I'll give you guys until 11:34 to do this. So you'd want to remember that with these sort of mixing problems, it's always inflow minus outflow. So this is some initial condition here. Fresh water, so being told that the amount, so the mass of salt that goes in is 0, and that goes in at 10 liters per minute. 10 liters is removed per minute as well. Okay. Hope that was enough time for you guys to have a go. Okay. Alrighty. So the first step here is to identify what our rate in. So identify that rate in was 0. This is our rate flow in, and this is our rate flow out. And this is just simply the amount, like the volume change, right? So rate flow in is equal to the rate flow out, so there is no volume change. So dxdt is the rate of change of concentration. And so our volume is going to always be 100, right? So it's 100 times the rate of change of mass. And since what's going in is 0, all I have to do is sub my values in. And so rate out is equal to concentration times rate flow is equal to x times 10. And resolve, and this is what I get. And so the answer here was A. Okay, cool. I'll quickly just stop this poll. Alrighty. I think for the sake, like just in the interest of time, we're not gonna have a go at this question. The solutions are up, and so the ways to work through that question are up. I'd say have a go at that in your own time. Cool. All right. This next bit is talking about kinematics. I think. Yeah. So this is back to calculus and kinematics. That is out of order. Okay, that's probably not a good thing. Okay, so I'll get you guys to have a go at. So yeah, you guys can do this in your own time as well. I'll get you guys to have a go at this question here. So this one is just using Euler's method. I'll give you guys until 11:38. Okay. Hopefully you guys have had a crack at this. So show results. Okay. All right. So this is the table that I was talking about. So you want to create a table of x versus y, and then you want to sub in every single value and work out every single step until you basically get your solution. So I'm not going to run through that in too much detail, but the answer for here was B. Yeah, so yeah, so the answer for that one was B. Okay. All right, so I think where people went wrong was just understanding where the overestimate and underestimate bit was. I think that is also covered in the notes in a bit, so yeah. Okay. With overestimates and underestimates, that's a pretty niche topic. I'll probably send a quick email about that after the lecture, just quickly covering the differences. Okay. All right, so let's quickly go over some integration techniques. So we've got integration to inverse trig functions, integration by substitution, integration using trig identities, partial fractions and recognition, and so on. So we have multiple techniques. I'm not going to do this question either. This is just a volume of revolution question. So the trick with this one was just knowing what the formula was and then using partial fractions to simplify everything. Okay, so when we use our integration techniques, we want to use a variety of functions. We want to be able to identify the variety of functions that we can use. So when I say functions, I mean the different sort of steps that we can use, sorry. So the different sort of substitutions we can make, the different sort of formulas that we have at our disposal to sort of solve these. And so when we have a rational function with partial fractions, so when the degree of f of x is less than the degree of g of x, we want to use partial fractions. If they're the same degree, then we want to be able to break it up, and then we want to use partial fractions. And if the degree of f of x is greater than the degree of g of x, then we need to use long division and then partial fractions. So this question here, I think, was a pretty good example of case 2, this one here. So you can see that when I substitute this in and I square this, the degree of the numerator is equal to the degree of the denominator. So I'm going to have to use, I'm going to have to simplify it and then use partial fractions, which is basically what happens here. Cool. So then you can use partial fractions on this, because then this returns to case 1. Okay. So this is just a quick summary thing. So when we get our question, right, we're not going to straight away know what integration technique that we're going to use, right? So if there is a derivative and if they've, started building you out to this like overall answer at the bottom of the question. So, let's say it's like a 3 or 4 part question and you've taken the derivative of a similar function earlier in that question. Well, you're going to be using integration by recognition for that. If you're going to be using double angle formulas, or if there's a trig function, you're probably going to be substituting in you're probably going to be substituting in trig functions for that. If there is, like if you're trying to reverse chain rule, so if there's like a function that's being multiplied in, or there's a function that's being like divided, and they're sort of like derivative of each other, then you want to be using substitution. If it's two functions divided like this, if it's a quotient function, then you want to be using partial fractions. And so if you know you're going to be using partial fractions, you want to identify which of the cases you are using. Okay. If the function is a quotient function and it has a square root in the denominator, then you want to be using your inverse trig formulas there. So hopefully these make sense. I'd say have this in your summary book as well, and have these steps, I don't know, somewhere quite easily accessible. So whenever you do a question, you just follow all these steps here. But in exam 2, if there is an integration question, it's more than likely you can just chuck it into your CAS, unless they get you to show all the working out. So I'd say memorize these, maybe chuck them up as like a poster somewhere in your room. I think I had a similar poster in my room at the time that I'd always look at before solving a question. But yeah. Okay. I think I've got a couple questions based on which integration technique we're using. Okay. Okay, so for this one, have a crack at identifying which integration technique we're going to be using, and I'll talk through which one. Okay, hopefully that was enough time. I'll quickly show the results. Okay. So for this one here, it was your third option. We want to be using integration by substitution. So, show correct answer. Cool. So well done to everyone who got that. The reason we're doing integration by substitution is because this here is going to be the derivative of an inner function. So we can take the derivative of this, which is going to give us this. And so then we can reshuffle and solve. So we let u is equal to x is equal to 5, and that is our u sub. Because then we can get this bit here straight away, and we can let that equals u. And this ends up as our final equation. And then we can integrate this relatively easily. And we sub everything in, and don't forget your plus c. They do mark you down if you don't include plus c at the end. Have a go at this as well. We're not going to spend too much time on that one, just for the interest of time. I'll give you guys 30 seconds or so to have a crack at that. Okay. Show results. Okie dokie. So the first thing that we can do with this one is split it into two separate fractions. So with this, we'll be using 3 and 6. So well done to anyone who picked that one out. Yeah, so 3 and 6 for this. Because the first thing we need to do is there is a inner function here, and there's also a quotient function. So we can split this into two different equations. With this, we use trig, and then with this, we use a substitution because of the inner function. And let's quickly run through that. And yeah, that's your answer for that. Okay, so I don't have polls for this bit here. I'll quickly end this. Okay, so in the interest of time, I'm probably going to skip over these integration techniques, but it is definitely good to chuck these in your notes and have these as a few examples and cover this in your own time. So a lot of this is here just for your notes, but yeah, cool. All right, content block 3. Sorry, I think I just had this in to separate out the content blocks. Okay, so with content block 3, we mainly have kinematics, vector calculus, and dynamics. These are all pretty high yield topics, especially with dynamics and kinematics. They're asked quite a lot and tested quite a bit as well. So, okay, kinematics. So the first thing we want to know is what our motion variables are. So these are the ones that VCAR commonly uses. So X usually applies to position, V usually maps onto velocity, and A usually maps onto acceleration. Okay, so we have things like our vector values and our scalar values. So a vector value is, a vector value is a value that has direction and magnitude, whereas a scalar value is something with just magnitude. For example, the difference between velocity and speed is, like, if I see a car going in a certain direction and I say, well, that car is going 30 kilometers east, that's velocity because I've given a direction. But if I say that the car is just going at 30 kilometers, then it's just a speed because I haven't given a direction. Okay, cool. So all we have to do to find the other one is just take the derivative of the previous one. So dx dt is equal to v, and dv dt is equal to acceleration. And to get from, well, the other one to the previous one, you just take the integral. Okay, we also have average rate of change. If you guys remember this from methods, we need to talk about average velocity as well. So average velocity is just the change in displacement over some time, so x2 minus x1. Instantaneous velocity is going to be dx dt, so the derivative of position. And average speed is the total. So remember, keep in mind, there's a difference here. So this is talking about speed and this is talking about velocity. Average velocity is a change in position, right? x2 minus x1. Whereas average speed is the total distance traveled over time. Okay, cool. So quick note is that our units are in meters per second unless specified. And to convert it, we can use this conversion factor here. So I'd say have a conversion factor in your summary book as well. All right. So here's our average acceleration. So average acceleration, remember, acceleration is a vector property. So we need to have velocity, the final velocity minus the initial velocity over time, and that gives us our average acceleration. Our instantaneous acceleration, on the other hand, is just the derivative of velocity. Okay. It's important to note that the direction that we're going in is not our acceleration, right? The direction of motion is given by velocity, not acceleration. Like, you can be in a car, right? So let's say you're going up to a red light, and so you're going to slow down, right? So your acceleration is negative. So your acceleration is going behind you, whereas you're still moving forward. You're you're just slowing down. For example, another one is like, my hand moving to the right but slowing down. Technically, it's accelerating to the left, but it's still moving right. So this is an important distinction to make. So these are Suvat equations. You do need to memorize these. Have these in your summary book as well. But yeah, one cool thing you can do is have a go at deriving all of these in your own time. I think it's a pretty fun exercise. But yeah, okay, cool. So yeah, each equation is missing a variable that the other one has. So these, I think, are the most important ones. The others, so this one I've like barely ever used. Like this one hardly ever gets used because you can always use one of the other ones instead. I've used this one a couple times, but I've like almost never used this one here. Okay, so most Suvat questions happen in a single direction, except projectile motion. They're always Suvat related. You'll always have to use these equations. The horizontal has no acceleration, so you'll never have to worry about your acceleration bit. So the horizontal is always the same, unless there is air resistance. And they'll let you know when there's air resistance, and it'll be modeled as like a differential equation. Whereas in the vertical, your acceleration is always going to be equal to gravity. In Spec, gravity is usually 10 or 9.8, depending how they're feeling that year, I guess. But they'll always tell you. So other ways that they can ask you to, work out acceleration is using these. So sometimes they'll get you to map out a velocity times distance graph instead of a velocity times time or distance times time. And you're going to have to use this to work out your acceleration. This is a specific question type, right? So this is that specific question type here. I'll let you guys have a go at this question in your own time and then have a look at the solution. So you'd want to use either this or this. Both of these do simplify to the same thing, so it doesn't really matter which one you choose. But yeah, so for this one, it would just be easier to use this formula here. But yeah, I'll let you guys run through that in your own time. Okay. All right, so these are a couple of vector properties. So, the magnitude of a vector is equal to every component squared and then the square root of that. I'm probably not going to go through this. This is just some simple Unit 1, 2 stuff. This is for your notes as well. All right, cool. So here's the vector resolute equation, if I can get to it. So what a vector resolute is we're trying to find the shadow or the projection of vector A onto another vector. So we're trying to break down vector A into its separate components, effectively. So we're trying to break down A into its horizontal component and its vertical components here. It's like main question type when it comes to application is they want you to find the shortest distance between two vectors. And so you need to find W, basically. All right, so vector calculus is when we start putting variables into our vectors. And it's like kind of annoying to do sometimes. And it's how it's how physicists have decided to map out our world. We basically use vector calculus to map out the movement of 3D objects in space. We can apply calculus to them, and basically all the all the constant variables still remain constant. So nothing really changes when we apply calculus to vectors. So we just differentiate and integrate with every vector component separate, effectively. Okay, we can also apply some certain formulas. So I'd recommend having this formula in your summary book. So recall that the distance between two vectors is always going to be their positions and like the magnitude of the difference in their positions. And we can find that out using this. So we can use this formula here to work out the distance traveled. Remember to always take the magnitude of the velocity vector here. Okay, cool. The direction of motion is always given by the velocity. It's not given by the acceleration. It's not going to be given by the position, It's always by the velocity. Okay. So this is sort of like an important distinction. So two objects can cross paths, but sometimes they won't be at the same time, right? So this is like me heading to school and my friend also going to school. We're both going to sort of maybe take the same road, but maybe we'll be going at different times. But if my friend and I basically, leave at certain times and we end up on the same road at the same time, and somehow we both crash into each other, well, that means we were at the same position at the same time. And that's when a collision occurs. So same position, so the x's need to be equal, and the times need to be equal. Okay. Another sort of question type that they can ask you is shortest distance. And so you want to be using perpendicular. So perpendicular will always give you the shortest distance, and that's sort of labeled in this. Okay. These are the steps to sort of work through these short distance questions. Again, I'll let you guys have a go at these questions in your own time. Okay. I think in the interest of time, I'm going to skip through all this dynamics bit. All of this is also covered in previous lectures. So earlier lectures, I think in 2022, I think Meg runs them. She would have covered this in more detail as well. It's just that this lecture was meant to be more of a revision of Unit 4 primarily. But yeah, definitely have a look at those bits there. Cool. One thing I can get you guys to do is have a go at this multiple choice. I'll start the poll for that as well. Okay. This is the last question that we'll do today. And then I'll run through some tips and tricks for the exam. Okie dokie. Oh, okay. Don't think this one has a solution, which is kind of weird. So for this one, the answer was D. Okay. Momentum, it's sort of like another important concept. Again, chuck this in your notes. It's not in your formula sheet from memory. So here are some other questions you guys can have a go at. Here's some more questions to do with dynamics. But yeah, most of this section is just questions. Just in the interest of time, we're going to skip past them. But definitely do have a crack at these here. Okay, so your bound reference. So you want to be done with your bound reference before you start doing practice exams. But personally, what I did was I had my bound reference and my notes completed before starting practice exams. But I had a logbook. So I put a mistakes logbook and I collected all the mistakes and the difficult questions that I found in special exam 2s. And I stacked those into my bound reference as well. So on the day of my exam, which was really last minute, I basically binded these into my bound reference as well. Your bound reference should be highly personalized to you. So what worked for me, so me putting in like all these like old problems that I came across and, like difficult questions, that might not work for you. Maybe you would like a, sort of different strat. So it's just what works for you and not anyone else. You want to have information in your bound reference that's specific to you. Like, if you struggle with SUVAT, well, then you might want to have SUVAT in your bound reference. But if you know that you're really good with SUVAT, then maybe you don't need that in your bound reference. I had a lot of like calculator commands in my bound reference. Ideally, you want to memorize those as well. You don't want to have like a humongous bound reference because then you don't want to be flicking through all the tiny pages in your bound reference. Another thing is know where every bit of information in your bound reference is. Like, don't take in your textbook. Make it pretty personalized to you. So these are sort of my exam, I guess, like tier list. MAV and VCA and HT are probably the closest you're going to get to like VCA standard. But yeah, so I'd say do MAV exams, NEEP exams, and then as you're getting closer to your date, you do those VCA, and HT exams. And ask your teachers for more exams as well. They do have a bank of exams. So, yeah. And when you're marking your exam, be as harsh as you can on yourself. Don't be like, oh, well, I would have gotten this on your. I was like, oh, this was a silly mistake. I wouldn't have made this. Because ultimately, it does come down to silly mistakes that differentiate between the top students. It's not a matter of content. It's just usually a matter of who can make the least number of silly mistakes at that higher end. So you do want to get, rid of those bits. So yeah, try go to bed early every night. The more time you can sleep, the better your brain actually functions. Have a play around with your calculator. Explore every single different function that is covered in the course. TI Inspire has like a full manual online. There's people online who also make YouTube videos that basically run through every TI Inspire function. Teach your content to your peers. Like, you're not competing with other people in your school. You're competing between people in the state. So it's always good to help everyone in your school around, because that does change your school's ranking. And yeah, don't stress. At the end of the day, be confident with your preparation. Be confident that everything that you've done is, you've done it to the best of your ability. So yeah. So on the day of your exam, don't start thinking about things that you could have done differently to prepare for it. Just go into the exam knowing that you've done everything you can do, and you've done everything to the best of your ability. Just some exam specific advice. Use your reading time wisely. Identify the easy questions. Identify the hard questions. If you can't, if you read through a question, can't figure out what to do within 10, 30 seconds, move on and do it at the end. What I did was I tried to do every question until I worked through every question and worked it out till I knew I got it correct, and that only then did I move on. But what some people like to do is basically finish the question, finish the exam as quick as possible and then come back at the end and check. But again, that's up to personal preference. In exam 2, I'd say read your extended response first, and then leave the end for multiple choice. So 90 seconds to a minute to 90 seconds is pretty good for multiple choice. But yeah, try not to go above 90 seconds. For every question, I'd say set up a new problem tab. It just helps you keep your working out organized. If you don't know how to create a new problem tab on your calculator, I'd recommend doing that. When you do questions, define everything, define all those functions, and yeah. But yeah, this is why practice exams are good for you to develop your own preferred exam technique way. This is just some general exam advice, so highlight, underline, that sort of stuff. But yeah, so during exam season, I spent a lot of time reading. At the time, I was reading Dune. But yeah, go out for walks, hang out with friends. It's always good to de-stress during exam period.